Okay, so welcome back. So our sorry about the little bit late start. This is a problem due to Elms. I don't know why my Elms I couldn't log on any device until like 3 minutes ago. So anyway, in the future, if that happens, just like I said in chat, I'll just stream public, and you can just watch it from the channel without from the class YouTube channel without actually needing the announcement. But anyway, hopefully there's no problem with that. Okay, so we are now interested in. So we saw yesterday some examples of differentiable functions, and we saw that there was a lot that this discussion had in common with the early stuff you did in Calc 1 when you were first showing that certain functions had the derivatives that they do. So yesterday we actually showed a bunch of those differentiation rules that you're used to from the glory days of calculus. And so just to remind you, so we had the basic facts that the derivative of constant, and of course it's true even for a complex constant here, right? So when we say constant, we are talking about a complex number that's not changing. So the derivative of constant 0, derivative of the function f of z equals z is 1. Derivative of constant times a function of complex variable is constant times the derivative of that function. Okay, so constants pull out of functions like this. We have the linearity fact that the derivative breaks up across sums of functions. So derivative of a sum of functions is the sum of the derivatives. We have the familiar power rule. Okay, and this is true actually. I wrote it here for n is equal to z, or n being a positive integer here, but of course this is actually true when n is an integer just as well. And so the derivative of z to the n is n times z to the n minus 1. So you're used to that. The product rule, of course, kind of the key defining thing that makes the derivative behave the way that it does. This Leibnizian property is that the derivative of product behaves in this familiar way to you, right? It's not simply the product of the derivatives, that is derivative of f times g plus f times the derivative of g. Okay. And then we have quotient rule. This just follows from the product rule, so you can apply product rule and power rule here to get the quotient rule, but this is a nice convenient form of it that, again, you're used to from Calc 1. And we have the chain rule, right? Also a very, very important fact. So all of these rules combined, since the chain rule allows you to find derivative of compositions of functions, all these rules combined together allow you to find the derivative in pretty short order of a pretty wide array of functions here. Okay, and we saw some specific examples of functions and their differentiability properties, including some examples where some kind of weird things were going on, like so yesterday, in the previous lecture, we did this example for f of z is equal to modulus of z squared, and found that this thing was differentiable only at z equals 0, right? So this is differentiable only at z equals 0, okay, and nowhere else. For instance, this is one of the things that we saw. Now, it would be nice if we had maybe a convenient way of characterizing differentiability without having to go through all of those arguments in the style that we were doing yesterday. And so the question is, can we devise a convenient criterion for determining if a given f of z is differentiable at some point z naught. Okay, and the answer is yes, that's exactly what we're going to do. Okay, so that's exactly what we're going to do starting out here. Okay, So the setup for this is, let's recall we can write any complex valued function of complex variable as u plus iv, where u and v are functions of x and y, where of course z is x plus iy. Let's set up this notation the following way. So just like yesterday, so z naught will be x naught plus I y naught. Okay. When we say delta z, what we will mean is, or rather another way of thinking about delta z would be as delta x plus I delta y. Okay. Where this delta z is actually the same delta z that showed up yesterday. Okay, so remember delta z is z minus z naught. Okay. Okay, so thinking of it this way, remember that if we were thinking of w as being defined by the functional value at z, then delta w is f. It was the numerator in that difference quotient, right, that we rewrote. So this is f of z naught plus delta z minus f of z naught. Okay, so this was our numerator in that definition of derivative showing up yesterday. Now, if we rewrite this in terms of u and v and delta x and delta y, what does this become? So let's be careful here. This is not actually too complicated. We just have to be careful about regrouping here and being careful with our notation. So this is u, right? So this is u of x naught plus delta x in the x slot, right? Y naught plus delta y in the y slot minus u of x naught y naught. Okay, so that's what's here, plus I times a similar expression, so v of x naught plus delta x, y naught plus delta y in the x and y slots respectively, minus v x naught y naught. Okay. All right, so that's what I have there. Okay. So, this, keeping track of this, together with remembering that our definition of derivative yesterday involved a limit, right, as delta z approached 0 of delta w over delta z, right? This was an alternative way of rewriting that difference quotient yesterday. It was kind of a convenient abbreviation. So let's keep this in mind here. So maybe I'll do this so that it's on the page at the same time. And so my derivative of f at z naught is the limit as delta z goes to 0 of delta w over delta z. So if this exists, so if we assume, and this is a big assumption, I'm going to put a star here. So assuming this exists, then what do I know? Well, if I'm taking the limit of this thing, right, and so I'm taking the limit of this quantity. Here's delta w in terms of u and v. Here's delta z. Okay. Then what do I get here? Well, then f prime of z naught can be rewritten here as just using just taking the real and imaginary part of this thing and setting it equal to these things. I'm not going to rewrite the whole thing because it would take too long, but this is what delta W is in terms of U and V. Okay, then this is the limit as putting it in terms of x and y. This is the limit as delta x, delta y approaches 0, 0. That's the same as delta z approaching 0, right? Of the real part of delta W over delta z plus I times the limit of delta x as delta x delta y approaches 0, 0 of the imaginary part of delta W over delta z. Okay. Okay. And so, keeping in mind that here's delta z, here's what delta W is if I break it down into its UV components like this. Okay, what is the idea? So, just like in those specific examples we did, there's a fundamental idea that's important here. Recall from yesterday's lecture, this is lecture 8, that we are allowed to have delta x, delta y approach 0, 0 along any path. Okay. So another way of saying this, right, is that if we're going to be able to compute some limit, right, we would have to be able to do it along any path, so that if I actually get something out of one way of approaching it from another way has to yield the exact same limit. Okay. And if it doesn't, then there's a problem. So we used that to our advantage in yesterday's lecture to show that some of these functions that we looked at didn't actually have derivatives at a lot of points. So an example of that is like z over z bar, right? Or actually, I think in yesterday's lecture, the example that we used was just z bar, right? So f of z is equal to z bar. We showed that that thing didn't have a derivative or wasn't differentiable at some points because we actually just, in the difference quotient, we ended up with some expression like z bar over z. And we showed that approaching from different directions yielded different limits, so this thing couldn't have a derivative. And so the idea here is exactly the same as yesterday. So my idea is to let delta x, delta y go to 0, 0 along the x-axis first, then do the same computation by letting it approach along the y-axis. Okay, so that we did yesterday was not just a single one-off trick that works in that particular instance. This is a nice trick that is pretty common and comes up in a lot of examples. So this is actually going to come up in our derivation of our main criterion of differentiability. Okay, and so let's do that. Okay, so let's do this along the positive x-axis. So the idea is exactly the same as yesterday. We have a point here. Of course, a point there is a point delta x 0, and we let it approach 0, 0 along the positive x-axis. And then next, we are going to let the point 0 delta y approach this point along the positive y-axis. Okay, but we're going to do the x-axis approach first. Okay, and so along the x-axis we have a point delta x 0 approaching 0, 0, which of course is the same as delta x approaching 0. Okay, and so in this case, what is the limit as delta x, delta y approaches 0, 0 of, let's look at the real part of this thing. So I'm going to box this, and let's look at each of these components. So let's look at the real part of delta w over delta z. Okay, and let's be careful with what's going on here. So remember, what we have here is the following, right? So here's our u and v components. But I'm looking at the real part of delta w over delta z. And so this part is not in my consideration because this is the imaginary part over here. So the real part just concerns this. So I have this expression divided by delta z, but along the x-axis, this delta z is just going to be delta x. And so what this becomes is the limit as delta x approaches 0 of u of x naught plus delta x. Delta y is equal to 0 along the positive x-axis, so this is y naught, minus u of x naught y naught divided by delta x. Huh. What is this? You've actually seen this expression before in Calc 3, right? What is that? Well, this is just u sub x, x naught, y naught, which is one way of writing the x partial of u. Right, this is the first order partial derivative of u of xy with respect to x. Okay, so maybe you're mostly used to seeing this sort of notation, del u, del x. Okay, we're going to, for convenience sake, it's nicer to use subscripts here. It's a lot more compact, a lot more manageable as far as the notation goes. So u sub x, which is the x partial of this function of x and y. Okay, at that point, x naught, y naught. Okay. Similarly, if we approach along the y-axis, what do we get? So along the y-axis, what do I get? Well, I have the limit as, actually, sorry, I'm not going to do the y-axis yet. I didn't take care of the imaginary part. So still along the x-axis, this is continued. The limit as delta x, delta y approaches 0, 0 of the imaginary part of delta w over delta z. This is equal to the limit as delta x approaches 0 of, well, now just looking back to what's going on here, right, the imaginary part of delta w over delta z is this v component over delta z, which is just delta, this is just delta x along the x-axis, right? And that delta y is 0. Okay, and so this is v of x naught plus delta x, y naught minus v of x naught, y naught over delta x, which is again the x partial of v at the point x naught, y naught. And so, assuming that that limit exists, right? Assuming that, that is, assuming that my derivative actually exists at that point, what do I know? Thus, assuming f prime of z naught exists, then f prime of z naught we saw is, where did I put it on my, yeah, there we go. F prime of z naught is, the limit is delta x delta y approach 0, 0 of this real part of this difference quotient plus I times this limit of the imaginary part of this difference quotient. But we saw that this limit of the real part of the difference quotient is actually the x partial of u at the point x naught y naught. And we just showed that this limit of the imaginary part of this difference quotient is the x partial of v naught, or sorry, of v at x naught y naught. Thus, the derivative of f at z naught is the x partial of u at x naught y naught plus I times the x partial of v at x naught y naught. This actually gives us a way of computing that derivative in terms of partial derivatives of u and v. Okay, so this is very, very nice. Okay, and of course remember z naught is x naught plus y naught, or I y naught, so this is where the x naught and y naught come from. Okay. Now you might look at this and you say, huh, that's a little weird that actually you can compute this derivative by just taking the x partial, right? Seems a little strange because we haven't really, like why would it just, why would we be able to do this for the x partial and say not the y partial, right? So we're not done, right? It's true that assuming this thing exists that you can compute it in this way, okay, but we're not just interested in that question. We're interested in coming up with some condition that has to hold that guarantees that this derivative f prime z naught actually exists, okay? And so in order to see what that condition has to be, we keep going. So we did this analysis by having delta x, delta y approach 0, 0 along the x-axis. Now, let's let delta x, delta y approach 0, 0 along the y-axis. Because whatever we get out of this is just as valid as what we got by letting it approach along the x-axis. Okay. And so, if we do this, what do we have going on here? Well, I can actually rewrite some of what's going on here by basically noticing. So first, to help with algebra, I rewrite delta w over delta z in a way given by the following. So delta w over delta z along the y-axis, what does this look like? So we have to be careful here. So first of all, let's go all the way back. Yeah. So if I go all the way back to this expression, delta w over delta z along the y-axis, now delta x is going to be 0. And so we have this expression divided by, in each component, I delta y, right? And so I'm going to go ahead, well, maybe I'll write this out so that it's not too confusing. So delta w over delta z is u of x naught. It's u of x naught plus delta x, but delta x is 0 along the y-axis, right? So this is u of x naught, y naught plus delta y, minus u of x naught, y naught, over I delta y, plus I v of x naught, y naught plus delta y, minus v of x naught, y naught, over I delta y. Okay. Now, of course, here the i's cancel, but here they don't. So here I'm really multiplying this expression by 1 over I. Okay, how does that change what's going on here? Right? Well, this is really like me multiplying this expression without this I in the denominator by minus I. Right? And so here the i's cancel. Again, let me do this so you can see it on the same page. So here the i's cancel. Here they don't, but multiplying by 1 over I is actually, I can rewrite this entire expression as having minus I times this expression. And what I actually get here is that delta W over delta Z is equal to, this becomes real because the i's cancel out here, and so this part is actually the real part. So V of x naught y naught plus delta y minus V of x naught y naught over delta y. That's the real part of this expression. Plus, or sorry, not plus, this is minus I times this expression. So U of x naught y naught plus delta y minus U of x naught y naught over delta y. There we go. Okay. All right. Now we look at the real part of this and the imaginary part, and we take the limits, right? So thus the limit of delta x, delta y approaching 0, 0 of the real part of delta w over delta z is, so taking the limit of this real part, this is the same as the limit as delta y approaches 0 of v of x naught y naught plus delta y minus v of x naught y naught over delta y. What is this? Well, this is exactly the y partial of v at x naught y naught. Okay. Similarly, the limit of delta x, delta y approaching 0, 0 of the imaginary part of this difference quotient delta w over delta z is actually, so this is going to be the limit of this thing as delta y approaches 0. So this is minus u sub y x naught y naught. Right, so this is minus the y partial of u at x naught y naught. Okay. All right. Now, the big step, right? So now these must agree with the limits we previously found for real and imaginary part of this difference quotient. Well, let's just remind ourselves. So the limit of the real part of the difference quotient that we found before was the x partial of u at x naught y naught. And the limit of the imaginary portion, the imaginary part of this difference quotient, is the x partial of v. So then what this implies is that the x partial of u at x naught y naught must be equal to the y partial of v at x naught y naught. And the x partial of v at x naught y naught must be equal to minus the y partial of u at x naught y naught. So I get these two equations that must be simultaneously satisfied. These are known as the Cauchy-Riemann equations. And what we have just shown is that these Cauchy-Riemann equations must be satisfied if you're going to have f prime of z naught be exist. Okay, so these must be satisfied in order for so these must be satisfied in order for f prime of z naught to exist. So that is what we have shown. And this is just because we know that that limit has to equal the same thing regardless of what path of approach you used. Okay. All right. Okay. So this is the big fact here. Okay, so regardless of how they're stated, right, you can move this minus sign over here if you like. These are the Cauchy-Riemann equations, and if they are satisfied, or I should say, if this is going to exist, that's what we started with. We assumed that this is going to exist, and we showed that if it's going to exist, then this has to hold. The question is, if this holds, is that enough to say that the derivative exists? So can we do this backwards? The answer is yes. If you actually trace backwards through this argument, the answer is yes, this actually provides what you need. Okay, and so kind of putting that all together into the following theorem, okay, we have this criterion that we talked about. So suppose that f of z is u xy plus I times v of xy. Okay. Suppose also that f prime of z exists at a point z naught is equal to x naught plus I y naught. Okay, then the first order partial derivatives of u, xy, and v, xy must exist. So that's all of them, right? The x and y partials here. And, so they must exist, sorry, at x naught, y naught. And must satisfy the Cauchy-Riemann equations. Okay. Remember, the Cauchy-Riemann equations are u sub x is equal to v sub y, and u sub y is equal to minus v sub x. Okay. At x naught, y naught. Okay. Also, to compute f prime, right, f prime of z can be written as, or I guess I'll say f prime of z naught can be written as u sub x, x naught, y naught, plus I times v sub x, x naught, y naught. That's the x partial here. Okay. So this just wraps up exactly what we did in this fact. Now, I didn't mention the backwards direction. I'm going to talk about that in a little bit. I wanted to do a couple of examples first. So this is saying that if the derivative exists there, then what we get out of it is the Cauchy-Riemann equations, and this is a way of computing that derivative in terms of u and v. We're going to see that if we're careful with the assumptions we make, going backwards, then this is going to also provide us with sufficient conditions for differentiability. Okay, so conditions that guarantee differentiability. So let's do a couple of examples. So first example is our favorite. F of z is z squared. Now we actually already computed f prime here, so we know that if we compute f prime of z squared, this is 2z, just from yesterday's rules. And so we're actually done already if that's all we wanted to do. But what we want to do is actually check that this satisfies this above theorem, satisfies the Cauchy-Riemann equations at some point, and so on. Okay. And so if we're going to do that, let's recall, right? This is me writing x plus iy squared here. And so expanding this in terms of u and v, I have x squared minus y squared plus 2 or I times 2xy, right? Yeah. So that u of xy is x squared minus y squared, and v of xy is 2xy. Okay, so let's check that this satisfies the Cauchy-Riemann equation. So let's take the x partial of u. So what is the x partial of u for this f? This is 2x. Well, let's take the y partial of v. What's the y partial of v here? Oh, 2x. Okay, so that part, half the Cauchy-Riemann equation is satisfied. Let's do the other two. So what is the y partial of u? That's minus 2y. What is minus the x partial of v? Well, minus 2y. So this satisfies Cauchy-Riemann equations. But what about this alternative way of computing the derivative here? Well, I claim that I can compute f prime of z as the x partial of u plus I times the x partial of v. So this is x partial of u plus I times x partial of v. But what is that? The x partial of u is 2x, so this is 2x, plus I times the x partial of v is 2y. So this is 2x plus I 2y. If I factor out a 2, this is 2 times x plus iy. Oh, but x plus iy is just z. This is 2z. But that's exactly what we already know the derivative to be. So this does, in fact, work nicely. Okay. All right. So let's do another example of this. So let's go back to one of our other favorite examples, modulus squared. All right, so f of z is equal to modulus z squared. In this case, what is u and what are u and v? So u of xy in this case is actually x squared plus y squared. And the imaginary part is actually 0 because this function is actually real valued, right? Okay. Well, what would it mean for the Cauchy-Riemann equations to hold? So let's just check real quickly. So we would have so first of all, the x partial of u is 2x, right? And the y partial of v is 0 because it's just constant 0. Okay, before I go on with this, I'm going to look at the y partial of u. So y partial of u is 2y. And so the x partial, or minus the x partial of v, is also going to be 0 because it's just a constant 0 function. Okay. So only way for Cauchy-Riemann to hold is for u sub x and v sub y to be equal. That is, 2x is equal to 0. And u sub y to be equal to minus v sub x. So that's 2y is equal to 0. And if these two things are simultaneously true, this is only true for x equals 0, y equals 0, i.e. z is equal to 0. So the only place where the Cauchy-Riemann equations hold is when z is equal to 0. Thus, f of z could only be differentiable at z equals 0. And of course, we showed yesterday that it is, in fact, differentiable at z equals 0. But how would we show that, right? So using this kind of formulation. So I don't really have a way of going backwards here. I don't have sufficient conditions for differentiability yet, but I'm about to. Okay, so that is the idea with what's coming next. Okay, so then I have the following fact. So big question, maybe I'll do this on this page where I have room. So question, what is a sufficient condition to guarantee differentiability at a point? Okay. The quick answer to this is basically it is the backwards direction of the theorem that I just stated. We just have to be careful with exactly how we state it. So that's not what I said is not technically true. There's definitely a subtle difference that you have to keep track of, but it's in the same spirit. Okay, it's the right idea here. And so the answer to this question is going to be the next theorem. So the next theorem provides exactly what it is we're looking for here. Okay, and so what does this say? Okay, so basically what we need beyond Cauchy-Riemann being satisfied at a point is some conditions on continuity. Okay, so this is what we need. So we have the following theorem. Okay, so let f of z, which I'm writing as u xy plus I v xy, be defined throughout some epsilon neighborhood. So this is an open epsilon ball centered at some point. So some epsilon neighborhood of a point z naught, which is x naught plus I y naught. Okay, and suppose that firstly, the first order partial derivatives of u and v with respect to x and y exist everywhere in the neighborhood. The first order partials of u and v exist everywhere in the neighborhood. Okay. Secondly, that they are continuous at x naught y naught, and they satisfy the Cauchy-Riemann equations there. So these partials are continuous. This is a big requirement here. These partials are continuous at x naught y naught and satisfy the Cauchy-Riemann equations there. So just to remind you what those are. So this is u sub x is equal to v sub y. U sub y is equal to minus v sub x. Okay, so those have to be satisfied at the point in question. Then f prime of z naught exists, and f prime of z naught is equal to u sub x at x naught y naught plus I times v sub x at x naught y naught. Okay. All right. Now, could you compute this with the y partials using the Cauchy-Riemann equations to substitute in here? Yeah, definitely. But this is an easier way to remember it because there's no sign change required. Okay. All right, so I'm not going to prove this theorem. It's mostly bookkeeping to actually make sure that you can go backwards through that work that we did previously. There's some standard analysis arguments that work that rely on the fact that you're assuming continuity. Here, this is actually the big key subtle point that we kind of missed out on and didn't really pay much attention to because we were assuming in the previous theorem that the derivative existed at the point. When you assume the derivative exists at the point, well, what do you have, right? You automatically have continuity at that point. So the fact that it's continuous at that point is kind of hidden in the assumption that you're making. Okay, so then going backwards, you need this continuity at that point to make this work. Okay, so like I said, I'm not going to do the proof of this, but it's not. You can read over that yourself. It's not too crazy. And so let's do a couple more examples of this. So if we wanted to show, for instance, that the exponential function is differentiable, say everywhere, right? So here, let's look at the function f of z is e to the z. So if we want to show this thing has a derivative everywhere, of course, if z is x plus iy, we can think of this just as well as e to the x times e to the iy by splitting it. Okay, so then rewriting this using Euler's formula, this is e to the x cosine y plus I times e to the x sine y, right? It's another way of rewriting that function. Okay, so rewriting it like this then, u of xy is e to the x cosine y. That's the real part of this. The imaginary part is e to the x sine y. Okay, let us verify that the Cauchy-Riemann equations are indeed satisfied. So what's Cauchy-Riemann equations here? So, well, first of all, we need to compute all the first order partials. You know that. So the x partial of u is the x partial of e to the x times cosine y. Well, cosine y gets treated as a constant when I'm taking the x partial. This is the x partial of e to the x. That's just e to the x. So this is e to the x cosine y. Okay. What about v sub y here? All right, so what's v sub y? Well, v sub y is, now I'm taking the y partial of e to the x sine y, so e to the x is treated as a constant. The y partial of sine y is cosine y, so this is e to the x cosine y. Hey, we're happy there. Okay, and so let's compute the y partial of u. So the y partial of u is going to be y partial of e to the x cosine y. So this is e to the x treated as a constant. So the y partial of cosine y is going to be minus sine y. So this is minus e to the x sine y. And minus v sub x here is it's minus the x partial of v. The x partial of v is going to be x partial of e to the x sine y. So that's just e to the x sine y. So this is minus e to the x sine y. Hey, there we go, right? So Cauchy-Riemann equations are satisfied there. And notice that these derivatives, all these derivatives that we took, these are continuous functions because they're products of continuous functions in variables x and y. Right? So these are all continuous. So these are all continuous. They're actually continuous everywhere. These are all continuous everywhere. and satisfy Cauchy-Riemann everywhere. So what does that mean? So this means that f prime of z exists everywhere. Okay, and we can compute f prime of z as u sub x plus I v sub x. Well, u sub x is e to the x cosine y. V sub x is e to the x sine y, so it's plus I e to the x sine y. Hey, right, this is exactly e to the x e to the I y, which is e to the x plus I y, which is e to the z, which I already knew, right? I already knew. That's the derivative of e to the z. Okay, but this is just reinforcing it, right? Okay, now as I said previously, when we looked at this example, f of z, which is modulus of z squared, we saw that looking at the Cauchy-Riemann equations, the only place this could possibly have a derivative is a 0. But this is actually going to this is going to give us the exact differentiability criterion and say that it actually has that derivative at 0. Okay, so again, remember that u here is x squared plus y squared, and v is 0. Okay, so this satisfies Cauchy-Riemann only at 0. Only at 0. Let me rewrite that as equals 0. Okay, but the derivatives here, the partials, are all continuous, right? So the x and y partials of v are both 0, because it's just a constant function of 0. The x and y partials of u are 2x and 2y, respectively. So all those are continuous everywhere. They only satisfy Cauchy-Riemann, however, at at z equals 0. And so because they satisfy Cauchy-Riemann there, and because they're continuous everywhere, this thing is actually differentiable at, so f prime of 0 exists, and f prime of 0 is equal to u sub x of 0, 0 plus I v sub x of 0, 0. V sub x is 0, so this is 0. U sub x is 2x. At 0, that's 0. So this is 0 plus I 0 or 0, which is exactly what we had computed from the definition yesterday, I believe, or the day before. Okay. All right. So I don't see any questions about that, so I'll move on to the next thing, which is to say this can come in handy sometimes. So the following fact, this criterion can also be stated in polar form. Okay. So it can also be stated in polar form. What do I mean by that? I mean, rather than thinking of f being expressed as these functions u and v that depend on x and y, I can think about them being expressed as functions of u and v in terms of r and theta, and I can actually derive the same kind of criterion in the Cauchy-Riemann equations. Instead of variables x and y showing up, it's the variables r and theta showing up. Okay. And so, how can I do this? Well, the idea here is, so same formulation as before, right? So if our z naught is not 0, okay, we won't worry about that. Then what we can do is use polar coordinates. So let x be r cosine theta, y be r sine theta. Okay. And then typically we would write z as x plus I y. Of course, in polar form, this same z would be written as r e to the I theta, right? And so I want to think of my function f of z as being written as u in terms of r and theta plus I times v in terms of r and theta. Okay. But then how can I manage this in the same way, or using the work that I already did previously, thinking of the u and the v in terms of x and y? So here I rely on what's called the chain rule from Calc 3. Which is funny because when I teach Calc 3, a lot of times I actually skip this. Well, I've had some bad luck the last few times I've taught Calc 3, and it is required material to be cut out and replaced with other stuff. And I think the last time I taught Calc 3, I didn't actually go over this section. It's like one tiny section in the textbook used. But this is one good use for it. So the chain rule from Calc 3 is a chain rule for multivariate functions. This isn't necessary if you reduce all of these to a single variable and actually do it using the chain rule in the Calc 1 sense, but this can be more convenient to track. So what the chain rule from Calc 3 says is, in particular, if I'm looking at the partial derivative of, say, u with respect to r, and u I know is also a function of x and y in addition to being a function of r and theta, then I can do this. You might remember, if you ever learned this, of following like a tree, okay, to actually keep track of what needs to be multiplied and added here. And so this is the x partial of u times the r partial of x, okay, plus the y partial of u times the r partial of y. The way that you're supposed to remember these formulas, so there's not just one chain rule from Calc 3. That's part of the thing. Like, it depends on the variable that you're actually computing the partial derivative of, what thing that you have to add out here. So I'm not going to go too much into that. The easiest way to remember these formulas is that just like when you reformulate the chain rule in terms of these Leibniz quotients, you're pretending like these are canceling out. And so you need to have a cancellation from both other variables that this thing depends on, so x and y here. So I have the x cancellation leaves me with del u over del r, and the y cancellation leaves me with del u over del r, and that's it. It's exhaustive because only x and y is all I need to describe u. And then the same is true for its derivative with respect to theta. So this is the x partial of u times the theta partial of x plus the y partial of u times the theta partial of y. Okay. Okay, and so this allows me to actually rewrite so u sub r here. So u sub r, that's just another way of writing this. This is u sub x, right, the x partial of u, times the r partial of x. But x is also a function of r and theta. So the r partial of x here is what? So this is just cosine theta, right? So this is u sub x cosine theta plus the y partial of u is just u sub y, and the r partial of y is sine theta. Okay, and u sub theta is the x partial of u, so that's just u sub x, times the theta partial of x. That is minus r sine theta, right? So this is minus u sub x r sine theta plus the y partial of u times the theta partial of y, which is r cosine theta. Okay. And similarly, we can say that v sub r, so using same formula, just replace u with v here. So v sub r is going to be v sub x cosine theta plus v sub y sine theta. And v sub theta is minus v sub x r sine theta plus v sub y r cosine theta. Okay. Then what happens if, assuming Cauchy-Riemann holds, recall Cauchy-Riemann means that u sub x is equal to v sub y, and u sub y is equal to minus v sub x. I can actually alter these expressions slightly. Okay, so using Cauchy-Riemann to swap out relevant terms here, what do I get? So then this implies, maybe I should keep them on the same page so you can see what it is I'm doing here. Okay, so then what do I get? So among other things, I get v sub r is minus u, so v sub r is minus u sub y cosine theta plus u sub x sine theta, and v sub theta is, so swapping these out, this is u sub y r sine theta plus u sub x r cosine theta. Once we've done that swapping, we compare these with these. And what do we notice? So comparing these two, what do we get? Well, we get that r u sub r, right, is equal to v sub theta, right? So if I multiply u sub r times r, this is exactly v sub theta. So r u sub r is equal to v sub theta. Okay, and what else? What's the relationship between u sub theta and v sub r? Well, there's just a minus sign, but this has an r and this one doesn't, right? And so u sub theta is equal to minus r v sub r. Okay. What is this then? What are these? This is the polar form of the Cauchy-Riemann equations. Why are we going through all this trouble? We're going through all of this trouble because the polar, so sometimes you have a function of a complex variable and it's given to you in a particular form, right? Maybe you know the real and imaginary part in terms of x and y, right? In that case, just the normal form of the Cauchy-Riemann equations is fine, but maybe it's actually given to you in polar form, right? So maybe it's actually given to you in terms of r and theta. And rather than go through what could be a potentially really nasty conversion, right, from that back to rectangular, this allows you, what we're going to say next allows you to apply the same fact in the form that you're given without having to do any extra work. Okay, and so we put this together, okay, to get the following theorem, which gives us an analog of this theorem we just showed for rectangular coordinates in terms of polar coordinates instead. So let f of z be in polar form, so it's u of r theta plus I times v of r theta. Okay, let this be defined in some epsilon neighborhood of the point z naught, which I am thinking of as r naught e to the I theta naught. Okay, and we have the exact same kind of statements. So suppose that first of all, first order partials of u and v with respect to r and theta exist everywhere in the neighborhood. And secondly, suppose that they are continuous. These partials are continuous at r naught theta naught and satisfy the polar Cauchy-Riemann equations, which is these. So r u sub r is equal to v sub theta. U sub theta is equal to minus r v sub r there. Okay. Then f prime of z naught exists, and f prime of z naught can be computed directly as e to the minus I theta times u sub r plus I times v sub r. I'm not going to go through the derivation of where this comes from, but I'm sure that you can figure it out just from the polar form of Cauchy-Riemann equations and exactly how we did this analysis in the previous theorem. Okay. All right. So what's an example of applying this theorem? So maybe I'll just do one example here. Okay, so here's an example. There's another useful example in your textbook that involves third roots, but I'll skip that one for now. So let's look at the function f of z, which is 1 over z. Okay, this is a function that doesn't necessarily have a nice rectangular form, but in polar form this actually isn't too bad at all, right? So if I write this in polar form, this is just 1 over r e to the I theta, which I can rewrite as 1 over r e to the minus I theta, which of course I can write as 1 over r times cosine theta minus I sine theta. Right, so this is an example of a function of a complex variable that has a nicer expression in polar form than rectangular form. Okay, so there it is. Okay, now what do I do here? Well, I note that u sub r theta is equal to 1 over r cosine theta, and v sub r theta is equal to minus 1 over r sine theta. Okay. So then let's actually check some things. So first of all, these are continuous, right? It's continuous for all z not equal to 0. We're not going to talk about z equal to 0 here. So this is continuous for all z not equal to 0. And so these are continuous everywhere. The partials are actually going to be continuous everywhere, but to see that, let's compute these things. So what is u sub r of r theta? All right, what's u sub r here? I'll actually suppress this notation. Next, so what is u sub r here? So this is just the derivative of 1 over r, so this is minus since this r is the minus first, this is minus r to the minus second, so this is minus 1 over r squared. Cosine theta, what is v sub theta here? Okay, so v sub theta is equal to, this is the derivative of minus 1 over r sine theta, so only the sine theta matters here, so this is minus 1 over r cosine theta. Okay. And so the question is, do we have the first equation from polar form of Cauchy-Riemann? So r times u sub r is equal to v sub theta. Is that what we have going on here? So if I multiply r times u sub r, is that the same as v sub theta? Multiplying by r, I get minus 1 over r cosine theta. That's exactly what I have there. Yep. So first half of Cauchy-Riemann equations in polar form are satisfied. Okay, let's look at the second half. So let's compute u sub theta. So u sub theta is going to be minus 1 over r sine theta. And v sub r is going to be 1 over r squared sine theta. And the question is, do we have u sub theta is equal to minus r v sub r? Is that what we have going on here? So minus r times v sub r would be minus r times 1 over r squared, so that's minus 1 over r sine theta. That's exactly what u sub theta is, so yes. Notice that all of these partials are continuous. So all these partials are continuous. They satisfy the polar form of the Cauchy-Riemann equations. So this f of z, or f prime of z exists whenever z is not equal to 0. So this thing exists whenever z is not equal to 0, and thus also, according to this fact, f prime of z, if I want to actually compute this, let's go back to my statement. This is e to the minus I theta times u sub r plus I v sub r. So u sub r here is minus 1 over r squared cosine theta plus I times v sub r, which is 1 over r squared sine theta. Okay. So let's work through what this actually is here. Okay, so this is actually, like, I can pull a minus sign out. This is like minus e to the minus I theta times 1 over r squared, pulling that out. Other than that, this is also e to the minus I theta. Okay. And so rewriting this, this is 1, so this is minus 1 over r times e to the I theta squared. All right, since this would be minus 2I theta here. All right, so moving that to the denominator. This is the same thing as minus 1 over r to the e to the I theta squared, but hey, that is minus 1 over z squared, which is exactly what I expect it to be, right? Okay. All right, so now that you've seen an example of how to use that alternative condition for this thing, it's finally time to define an analytic function. So what is an analytic function? So definition. This is analytic function. This is complex valued function. So I'm going to mention at the beginning of class next time some key differences between when I use this word analytic and when I use it for real valued functions. But I'm going to also explain why we are using the same word, because it's very important. What we're getting to now is going to be one of the fundamental things that shows you how different complex analysis is from real analysis. Okay, and it's an amazing fact when you think about it. So first, I'm going to define what an analytic function is. So a function of a complex variable f of z is analytic at a point z0 okay, if it has a derivative at each point in some neighborhood of z0. Okay. So analytic is the key word here. Now we have alternative words that can be used to describe this. So alternative terms. And it's actually important to make note of these alternative terms, because if you're doing any reading about complex analysis, these are used entirely interchangeably. The fact that they're interchangeable is actually amazing once you see what these things are actually equivalent to for complex valued functions. If you have any experience with what analytic means for real valued functions, okay, and if I go ahead and spill the beans and tell you that, this is what is meant, this same fact is actually true when we say analytic for complex valued functions, then already you might be amazed. But if not, then you can save your amazement for next time when I'll explain what that fully means. But alternative terms here is the notion of f being holomorphic at z0. So maybe you think holomorphic sounds cooler than analytic. So you can definitely use holomorphic instead. Holomorphic means the same thing as analytic. Another term is f of z is regular at z0. Okay, so being regular at a point, being holomorphic at a point, this is the exact same thing that we're calling being analytic at a point. Okay, f is analytic on an open set if it is analytic at every point in the open set. Okay. Okay. Which means it has a derivative everywhere in the set. Okay. So if we mention that if we say that f is analytic on some closed set, then what we mean is that it is analytic on some open set that contains that closed set. Since if it was analytic on a closed set, because analytic requires it to have derivatives in a neighborhood, right, then this is necessarily going to require the function to be analytic on an open set containing that. You can just cover the entire closed set by those neighborhoods. Okay. All right. Okay. I'm going to give a couple more terms, and then that'll be that. So we say a function f is entire if it is analytic on the entire complex plane. Okay, this is the notion of an entire function. Now, you might be a little bit confused that we're introducing another term here, period, because you might say, wait, if analytic just means that it has a derivative in, at all points in the neighborhood of some point, and entire means, it has the derivative everywhere in the entire complex plane. That used to just be like for real functions that say had derivatives everywhere on the real line. We didn't have another word for that. We didn't call them entire. We just said that they're differentiable everywhere, right? So why don't we just say that here, right? Because it's true. If something's analytic on the entire complex plane, it's differentiable everywhere. Then so why come up with a new word? It's to stress the difference between having a derivative for a complex function and having a derivative for a real function. This is the key difference in complex and real analysis, is that having a derivative as a function of a complex variable is a lot stronger. It's a much more powerful fact than having a derivative as a real valued function. What I mean by that is if a function of a complex variable is differentiable everywhere, or if it is even if it's not differentiable everywhere, if it's analytic on some open set, that is it makes that function much nicer than saying the analogous thing in real analysis. So you can dream up, you're probably already thinking of examples of real valued functions that have a derivative somewhere, right? So there's a huge class of functions that entails. But you can actually dream up some pretty nasty functions that have a single derivative, right? Maybe they don't have more than one derivative. We haven't mentioned anything about higher derivatives. But there's a big difference between these two. And I'm going to talk a little bit more about that next time. So anyway, this is the terminology that you need for now. I'll post your third homework sometime late tonight, and it'll be due like Monday at midnight. And then at the end of next week, I will post your first midterm, which is kind of be like a compilation homework almost. It's just going to be some different questions from everything that we've done so far. Okay. But questions, it's mostly overall kind of similar to the homework, but I will just basically select some of the things that I didn't put on the homework. Okay, so anyway, that's that. I will see you all on Monday. Oh, and I also mentioned I'm doing office hours a little bit later. So I'm doing office hours later here in like a few hours, or like 2. I'll send the link like right before I do it. So anyway, I think that's that for now. So I will see you all later. Let me see. Is there no questions in chat? So anyway, if you have any questions about the homework or just questions in general, swing by the office hours. Like I said, later today. So I will see you all later.